Today, we are going to have a conversation about AI and manufacturing, and I am joined by some amazing colleagues. Number one, Nasir Mannan, who is our principal engineer and head of a lot of our work that we do at the Advanced Technology Center. And we're joined by two other colleagues who are newer in their career paths, and including one former intern, Maliha, and Shriniket as well. And you're going to hear a lot of great information from them shortly. Just a reminder for everyone to please put any questions into the chat box or into the Q&A. We will most likely answer those after the bulk of the presentation is completed. And then I'll wrap us up with a couple of pointers about some upcoming events and information for any of you who might be new to the internship program, because I know we've had some newer people join us. So thank you so much. And Nasir, back over to you, and thank you.
Great, thank you, Eileen. I appreciate that. Good afternoon, everyone. Thanks for joining. As Eileen said, I'm the principal engineer here at the Connecticut Center for Advanced Technology. And I'll give you a little bit of background about myself, and I'll hand it over to my colleagues, Shriniket and Maliha, to introduce themselves. But a little bit of background on me. I've been with CCAT now for 18 years. Prior to coming to CCAT, I was at Pratt & Whitney. My background is mechanical and software engineering. I'm a Connecticut graduate. I went to University of Connecticut, and then I went to the Connecticut campus for Rensselaer for my graduate degree. And I've been in the area for over 20 years. So our primary work here is to help advance manufacturing. We're a applied R&D center where companies can come to learn about the latest and greatest in technologies and what they could be using to really drive efficiencies through their businesses. You can think of it as for the small and medium-sized companies that are producing parts that go on aircraft, that go on submarines, that go on pretty much any kind of manufacturing, even in medical devices and in other applications. We're really here as a resource for those companies to come to our lab and to see how they can use software to save time, improve product quality, and really just be globally competitive. With that, I'd like to hand it over to Maliha to introduce herself, and then to Shriniket to introduce himself.
Thank you, Nasir. Hi, everyone. My name is Maliha, and I am a graduate from Southern Connecticut State University. I started here at CCAT as an intern in summer of 2023, and I did my degree in computer science and bachelor's. I graduated last year, summer of 2024. I started as a software developer on the same team. And now I'm also doing my master's back at the same university in master's in computer science. And I work with a lot of projects. We do a whole lot of things based on web applications, some machine learning, some IT work, and it's a mix of a lot of things that I work on.
Shriniket?
Hello, thank you for the introduction. I'm Shriniket Mchuri. I'm a mechatronics engineer at CCAT. So a bit about my background. I've been working here for about just under 3 years, and I graduated with a degree in mechanical engineering from the University of Maryland back in 2022. My work here it's a pretty wide berth of things that I work on. It ranges from stuff like running the machinery in shop for inspection and for like part quality and process optimization. And I also work on machine learning models for optimization of process parameters. We'll get into that a little bit more in this presentation, so I'm just going to leave it at that for now.
Great, thank you, Shriniket. So as Eileen mentioned, our subject today is to talk about artificial intelligence, more specifically how it relates to manufacturing. And we'd like to discuss how we're presenting it and how we're showing the value of artificial intelligence as it relates to manufacturing here at CCAT. So we're actually employing a number of different subjects within the broader, artificial intelligence umbrella. We're looking at using generative AI, and Maliha will talk to you specifically about what that subject is. We're also employing retrieval-augmented generation, which is it's a way to constrain AI to answer and give you responses out of information that you give it. So if you have a user manual and you have a specific question about a product, if you use retrieval-augmented generation, you can type in a question and the AI will respond to you from references that it grabs from that documentation that you give it. So there's traceability there. We'll talk more about that. And then there's the subject of machine learning. And machine learning is a very big, subset. There's many different algorithms that are contained within machine learning. But what we're doing here at CCAT and how we're leveraging machine learning for optimizing manufacturing processes is by collecting real-time data during the manufacturing process. And then we're able to train a predictive model, which allows you to predict what the feature dimensions are going to be as you're producing the part. So instead of finishing the manufacturing process, then inspecting it, and then finding out if the part is good or bad, we can actually determine if the part's going to come out good or bad while we're producing the part. And if we're in that state, then what we can do is we can also then say, okay, if it's going to turn out bad, what's going to turn out bad? And what's the cause of it going in that direction? And what can we do to change the parameters on the machine to make to bring the part back to within spec? So what this allows us to do is basically have a supervisory control over the manufacturing process. So we're nearly guaranteeing that any part that we produce on that machine is going to come out good. So Shriniket will talk a lot more about that and the work that we're doing here and how that system is specifically set up at CCAT. So with that, generative AI at a high level is the use of what are called large language models. And if you think of the internet, all the information that's contained on the internet, it's not all relevant, but it's the vast majority of that information has been used to train language models. And these language models basically are an algorithm that can take in natural language as an input and output a natural language response. And the information that it's been trained on is very vast, and it's not necessarily traceable. So if you were to ask a question to generative AI, and generative AI, you can think of it as a black box, right? You have this large language model, which takes the input, right, a question, and when it gives you a response, you do have to double check that response. And there's ways in which you can constrain the response and how it's, the subjects that it's constrained to for its response to you. Maliha built out an application using large language models, specifically OpenAI's large language model, ChatGPT. And she's going to describe to you in a little bit more detail and show you a use case of how we use generative AI to actually optimize and automate an otherwise multi-week process that we used to have to go through that now happens in just a few minutes.
So this is the project that I was working on when I transitioned from intern to full-time. It's a web application that uses large language model to help manufacturing company optimize their time. Normally, what would happen is when a solution provider would go in with a clipboard paper to assess a company's what they're using and what softwares and stuff like that. and come back and create a specific solution plan for their company, and then go a little back and forth with buying that plan and purchasing, billing, all that stuff takes up to months at max. But this application takes up to 30 minutes max. It cuts down the months of process into minutes. So there's three types. I'll go in a little bit of high level overview of what this application does. There's three types of users that uses this app. One is just an app admin that approves the company admin, which is just a regular user that adds in their company information. And this is just to vet that it's a legit company. And then there's a regular user. The difference between regular and company users is that company user would invite users between their own companies, and the regular users don't have that functionality. But this app has three main portions: business, technical, and a workforce. So it's based off of questionnaires that a user will fill out. They will fill out with their information, their job, their area of focus, what their company does, and what AI does. It takes on that information and it takes their answers. And then I added in a prompt so we can just contain the information. We don't want it to spit out everything. So we contained the information and we asked it to give back 10 most used softwares between the areas of interest. And it will spit out a plan of action for technical. Workforce works the same way. Instead of the softwares, it will give out a list of trainings, conferences that person can use to optimize their skills. And then for the business, it will just like a billing, it will work as a billing page where they can buy the software plans and they can register for the different conferences and different trainings that they can do. So this all process just takes max like 30 minutes. And there's so many different benefits from this. It saves times on both ends, from the solution providers, from the company people. They want to optimize their time. And this is a great application that uses OpenAI's newest model to generate the tailored results tailored specific to that employee using this application.
Thanks, Maliha. So with that, I'll just reiterate what Maliha said. It would take us, the tech team, the engineers, a good solid month to do what we call solution determination. We walk into a company, we try and understand their processes, we sit down and have meetings with them, and it's all to understand where's their pinch point, where are they not optimal in their manufacturing process. And then what we do is we talk with our tech partners and we come up with a solution. So if they're having problems with producing enough parts, what is the right software that they can employ to help streamline that process? If it takes them days to do programming or months to do programming on a part, is there software out there that can do it in minutes, right? But for us to do that manually for each company, it takes us a long time. And what Maliha created is a nice interface where a company can go and log in, answer a few questions, and then the tool automatically will respond with the appropriate solutions for that company. So what used to take us months, weeks to months, now takes us literally minutes. And that's a very a good use case for, specifically for generative AI. And in the context of how, we're leveraging the work that Maliha has done, we're actually offering this as part of our digital enterprise cloud business plan. And what this is it's just it's a multi-layered solution. And this application that Maliha developed is one of the main solutions that are contained within this business plan. But you can see that, I've listed here on the screen the adoption barriers that are being addressed by the solution. So, a company who has a pain point may not know the value of certain kinds of software or certain kinds of workflows that they could be employing, kind of getting away from their normal daily routine and then changing it to a new, more optimized routine. There's always a barrier. Companies may not know some specific technology exists that could be helping them today. And that's one of the major barriers. The other barrier is, okay, I know that the software can help, but I don't know how to use it. And then the other barrier is, okay, I understand that there's software out there. How much does it cost? And am I going to be able to afford it? Well, the solution to all of this is contained within the application that Maliha developed. And again, it uses generative AI to provide that solution. So you could see the multi-layered solution here on the top left. Sorry, at the bottom left is the plan of action tool that Maliha is referring to, and the solution that she's developed. It gives you the technical, workforce, and business plans of actions, like within 15 minutes, at most half an hour. And it will link to all of these other layered solutions that we can offer to the manufacturing supply base. So with that, I'd like to switch over now to another subject, another subclass of artificial intelligence called Retrieval-Augmented Generation. And this particular subject is very interesting because in the previous example, when we talked about generative AI, we talked about an AI system that has all this information that it's been trained on, and it's able to give you responses, but you don't have traceability. You don't know where it's gaining that information, where it's gathering, how it's responding to you, and what are the sources from which it developed its response. So this can be problematic for actually many subjects. If you need traceability and if you need to know specific information, this is where retrieval-augmented generation really shines. And as I mentioned before, it's a way for you to have essentially a database of information. And when I say database, it's essentially a location where you have a lot of documents that you give to the system. So let's say that, I mean, for connecting this to daily life, let's say you had a user manual for your TV. Let's say you had a user manual for your electronic devices, whatever they may be. Let's say you have a user manual for your vehicle, and you come across a problem, the TV's not turning on. Well, this is a good place where you can go into a chat-like environment, and you can actually ask it a question. Say that, I have this TV and it's not turning on, and you can give it some other bits of information, like the plug is in, the power's on, things of that nature. And you can say what could be the possible problems and hit enter. And then it'll give you a response, but the response will be from the user manual specifically. So it won't be generic. If you didn't use retrieval-augmented generation, it would give you a more generic answer that might not be completely applicable to the type of TV that you have, the specific make and model. But if you use retrieval-augmented generation and you give it a source like a user manual, then it will retrieve information from that source. So AI becomes a front end for the person to interact with, to ask questions and receive responses. But on the back end, you have this, you have this database, this vetted database that you put information into. So with that, that's a high-level overview of retrieval-augmented generation. And I will hand it off back to Maliha to talk about how we're using it here at CCAT.
Thank you, Nasir. So RAG, Retrieval-Augmented Generation, it's this application, it also is, you can call it that it saves time on reading up the documentation. And as Nasir mentioned, the process is very simple. It starts with a knowledge base, which its initial knowledge, it comes from the PDF, manuals, or any kind of documentation that you can feed in. So here I'll just go about a little bit of how the process works. And so initially you feed in the documentation, but then those documentation are passed through a model which turns the text into a numerical representation the AI can understand and search through. So those numbers are stored in a special database called vector database. And now when a user asks the question, this is how the system processes it and check the documentation to answer the question. This way we can limit AI to think of its own and give us answer based off of the documentation and have a vetted source rather than just searching the internet. And then next slide, I can show the use case that we have here at CCAT. So we're using RAG for automated quoting and part classification verification. So we're feeding in a document that is based off of part information and it has how the part is classified. And from the user's perspective, they create an account, they add a part information, all this part information that's described in the photo, part description, dimensions, properties, classification, and all the company information. And it will add the process and it will match the number with the documentation and it will say if it's approved or not, but it will not show that to the user. It will say pending. A human will go in and approve or disapprove because at the end of the day, we need to vet the information if it's right or wrong. So a human will come into the loop and approve or disapprove that part. We have a lot of different type of works on different type of machines, and it saves a lot of going and reading at each part and their number and matching to the documentation, going back to the person. Sometimes user or people mix and match the part and the number, and it saves a lot of the time and optimize the approval process for all of these different parts. Back to you, Nasir.
Thank you, Maliha. So the last subject that we're going to talk about here is machine learning. And this is yet another subset under the broader artificial intelligence umbrella. Machine learning is very powerful. It can take and process a large data set. We call this big data, where you have, hundreds, if not millions of lines of data, which would otherwise take a very long time to manually process. Machine learning does it in a very efficient way. So some of these algorithms are, you would know them as normal mathematical models, like, for example, line fitting, right? You have a bunch of points and you want to fit a line to it. That's called linear regression. Or if you have a bunch of points and you want to fit a curve to it, that's polynomial regression. These are typical mathematical algorithms that you would normally use, and it doesn't fall under the machine learning banner. But when you have a lot of data and there's a lot of noise contained within that data, the similar or almost the same output that you would get from these math models, you could actually use machine learning to have it to train a linear regression model or train a polynomial regression model to get you a very accurate line fit or curve fit on data that you otherwise would have a hard time processing because the amount of data plus the amount of noise within the data. So the machine learning subset, under AI, it does a very nice job, and it's pretty much automatic. There's some parameters that you have to tune. These are called hyperparameters, and those are, you can think of them as essentially options for how you want the algorithm to perform. So you would go through and tune or change these options and see the resulting accuracy, right, of the model fit. And then once you've attained a reasonable accuracy, then you can use that model for prediction purposes, for forecasting purposes, and for other applications. So it's an incredibly powerful subset within the artificial intelligence banner. And I'm going to hand it over to Shriniket, who's going to describe to you how we're using this subset here at CCAT.
Thank you, Nasir. So so I'm going to start off with basically our pipeline, what our workflow is for setting up our various ML models and what we're using them for. So I believe that you can see on the right, there is a MBD model. So MBD stands for model-based definition. And essentially what that means is you take all the information related to the product lifecycle management of that part. So for example, how it's manufactured, what its use cases, and its post-use. And you put all of that information into a source of one truth so that you can use that as a reference for any process at any point in the product lifecycle. So for example, on the right, it's giving you all the dimensions and all the tolerances of the part, but also it's going to have the information of machine cut paths, roughing and smoothing operations, and stuff like that. So all that information allows us to use it as a reference. Next, you need stock material information for the AI model, because based on the shape of the stock and the dimension of the stock, the cutting operations might be different. And that would also be reflected in the model-based definition as well. And then we have information coming from the edge device slash the PLC. So basically, this is information recorded in real time by the machine and saved onto a temporary drive that we can use as machine signal data. So machine signal data covers basically everything that the machine knows about its current position, torque, power, current, all of that, energy usage, everything. As well as it's like the spindle position of the spindle, for example. In this case, it's a CNC. And then we, of course, have the production system. So we have various different machines at our shop. In this particular example, we were using a CNC, but we have tried this process digital twinning on other machines as well, including a 3D printer. It's a metal additive 3D printer. As for the model, we will be training it on the data coming from our various parameters. So basically, we use these parameters as hyperparameters in our model. So Nasir did mention hyperparameters earlier. Basically, we are using these hyperparameters to, and we're trying to weight them to see which ones are more important for predicting the model. In general, this is the most difficult step of any ML process. It's thinning down the number of relevant data streams, because often what you're getting from the edge device is a massive list of variables. For example, in this part, we got a list of around 92 different variables. And realistically, in any ML model, you do not need that many data sources. Most of the time, there's only going to be a few that are relevant for computing an accurate prediction. So the first step is to narrow down what is actually important. And you could do that in several ways. You can either do it through trial and error by running different models and seeing which data ends up getting filtered out, for example, by a neural network. Or you can use physics, which I will get into later, to basically inform your decisions, and basically using the real world to inform your decisions on what data could or could not be useful. And then finally, we have the learners. So there is obviously a workforce aspect to this. So the person that is teaching or generating these models needs to understand how to consume them on the edge device, as well as how to train them. And of course, there's also inspection data. Inspection data is important for predictions, because even if you have all the machine data, all of that is pointless without some context. So if you're able to inspect the part and see which measurements are out of spec or in spec, you'll be able to use that as a benchmark for what machine signals are either basically inside of what you think they should be at that particular point in the process, or if there's a anomaly in the data that suggests that something went wrong in the process. Next slide, please. So this is the data I was mentioning for a additive metal process. So it's basically the same type of pipeline, but a different process altogether. So this is a there is basically a metal additive powder bed fusion printer that is printing out these sample parts. And essentially we are taking all of the data on the left. So this is all of the machine signals plus inspection data. So there's CT inspection data, and then there's a bunch of machine signals coming off of the machine as it's printing. And then we keep that in a user-friendly format, and especially a machine learning usable format. so that the computer can process all of this information and try to make porosity predictions. So basically, what the CT inspection is doing is it's trying to find pores that are forming for any various amount of reasons in a powder bed fusion process. This could be for from spatter from the melt pool hitting a different geometry. It could be unusual heat sink effect, because as the part is printing, there's going to be more material that the heat has to pass through, and that could mean more or less dissipation, as well as the print goes on for longer, there could be more heat stuck inside the material, which could cause warping and also pores. So what this is able to do is we're going to be using the CT inspection data as a baseline and seeing if there's any data from the machine signals going out of spec or doing something that we don't expect to happen, and seeing if we can correlate that using ML to predict where the pores are in process. So basically, as the machine is printing, we will be able to predict whether or not there's a pore at a certain spot. Basically, we're able to predict the quality of the part. Next slide, please. And this is what I mentioned earlier about using the real world to inform your machine learning model. So, for example, if you take this landing gear as an example, there's certain things that you know immediately about this landing gear. You're going to know what forces to expect, how cyclical these forces are going to be depending on the aircraft. So, for example, if it's a passenger airliner, you know that it's going to be used quite a lot and quite consistently. And you also know exactly where the forces are coming from and generally how strong those forces are and in what direction they're coming in. So you can use that information to rule out a lot of data that's coming in from your data streams. Because, for example, if you wanted to predict a crack propagation through your landing gear, you're not going to be using irrelevant data because, like, for example, if there's no torque forces on the part, you're not going to be looking at the torque or the geometry at that section for loading in torque as a reference for your ML model. And what UConn was able to do is they were also able to basically make a physics engine that is able to simulate the process as it happens. So we can use that instead of having to test it in the real world, which is obviously not very practical, very expensive, and it's not fast enough either. Because when it comes down to it, aircraft parts like this aren't produced very often or in high number. And as Nasir mentioned earlier, big data is pretty important for most machine learning models. So if you don't have a large amount of data, you have to find other ways to either source your data or to parameterize your input so that you need less data. Next slide.
So thank you, Shriniket. I appreciate you going through the machine learning subset. It's quite a vast subject. There's quite a number of different algorithms. And Shriniket really walked you through, our application of machine learning in manufacturing, like CNC, the application of machine learning for predicting porosity in additive parts, and then physics-informed AI, where we're trying to predict, feature dimensions on a small data set, and we're using, as Shriniket mentioned, a physics model to synthesize data that we would otherwise get off the machine, and then we're using that synthesized data to then train a predictive model once we calibrate it to the real world. And what I'd like to do is kind of walk you through, how we're using machine learning in a broader context at the Advanced Technology Center here in East Hartford. We're in the process of setting up an autonomous manufacturing cell. The key word here is autonomous. So everything that you've heard of so far, when you think of manufacturing, think of it this way. If a US-based company was to produce a part versus a foreign nation producing a part, a part produced outside of the US, what's going to be the cost difference, right? What we want to do is employ artificial intelligence here to essentially reduce the cost of the parts that are produced in the US. That makes us much more globally competitive. And this is really, using technologies like this will get us there, very quickly. And it's so much more beneficial to go the artificial intelligence route, or you can couple it with existing, physics-based, mathematical-based, statistical-based models to actually, further enhance what those specific, subjects can give to manufacturing in terms of process improvement, in terms of, at the end of the day, reducing the cost to produce parts. That's really what we mean by optimization. So the autonomous manufacturing cell is set up so that we can show the applications of all of the different AI subjects that we just talked about in one system. So you can see them all functioning together. And really the goal and objective of the autonomous manufacturing cell is to empower regional manufacturers with state-of-the-art technologies to establish a hub for research and development. Remember, AI is continuously being advanced, and we want to have, a cell that is set up to be able to test different AI models. How applicable are they, in our case, to manufacturing? And then to show the numbers, what is the cost savings? What is the time savings? What is the efficiencies gained by using these new advanced models? And then we want to enable testing and demonstration of key technologies that benefit from artificial intelligence. And then we're packaging solutions for the immediate adoption to the supply base. So when I say package solutions, I'll show you a chart of what exactly that means. But some of the key technologies that are going to be employed are data collection systems, like Shriniket mentioned. We need data. Artificial intelligence, obviously, as the main processing unit. Machine learning as a subset of artificial intelligence. Software development, of course, has to happen to connect everything together. Digital thread workflows, which allow automation of production programming. Process digital twins, which is basically the virtualization of your physical assets. So if I have a manufacturing system with multiple different machines, can I open up a piece of software that has all of those machines in 3D and functioning exactly the same way as they function in the real world, so that I can test different things in the virtual world before I put that test in the real world? That'll help to pre-vet some solutions and to avoid any, crashing or issues that may occur that can be costly in the real world. So that's what we mean by process digital twins. And then adaptive control systems. So as Shriniket mentioned, we're training models off of data that will allow us to predict if the current part being produced is going to come out good or bad, or for additive manufacturing, if the current part that we're producing in the machine is going to have porosity or not, and where the porosity is going to occur. And we do this for the purpose of correcting or changing parameters on the machine as it's making the part, so that that part comes out good, instead of finding out after the fact, once we produce it, that the part is actually bad and that we can't use it. In that way, we're saving a lot of cost, and we're actually driving the cost of manufacturing down, because if you were to produce 100 parts and 10 of those parts come out bad, you just wasted all that time and energy and cost that went into producing 10 parts that ultimately are not usable. So this is really the key benefit of when we say adaptive control units, to nearly, I say nearly, guarantee parts that to come out good off of manufacturing processes. These are some of the key technologies that we're focused on right now. CNC machining, inspection, welding, assembly, deburring, and some other ones. And when I say package solutions, what I'm talking about is there's different pieces of software that are used in manufacturing. So the part can start off in CAD software, and then once you have a design, that design has to then be manufacturable. You have to be able to make that part. So you go from the design into your manufacturing software, and that manufacturing software has to be able to read in the file format. And as Shriniket was mentioning before, the file format that we're most concentrated on is called model-based definition, because model-based definition is a computer consumable format where you have the 3D CAD and all of the product and manufacturing information embedded within that 3D CAD. It's not a 2D drawing that a human has to interpret. It's a digital format that computer systems and software can import and make decisions because all the information is there in a digital format that the software systems can make decisions on. But we have to guarantee, or we have to work out a solution so that the type of file goes from one system and gets exported out from that system and then successfully imported into another system so that that file can be used in that manufacturing software to its full advantage. Sometimes when you do file translations, you can come into a lot of problems and the file becomes unusable and you can't fully benefit, from this, what we call a digital thread workflow. So this software layer that I'm showing here in this slide is the work that we do at CCAT to come up with the solution of all the softwares that work together. We do a lot of testing, we do development if development is needed to get certain file formats to work. And we essentially put the time in so that the manufacturing companies don't have to go through that process to discover if a software is going to work with their existing software. We would have done that work for them. And then the workflow layer that I'm showing, the second layer down, that is showing how each software works and what middleware software might be necessary in order to have the digital thread workflow work. And then integrated hardware. So there's obviously, once you have your manufacturing process, that program that's generated out of the manufacturing process has to then be uploaded to the machine so the machine can actually execute and produce the part. But a machine always works with other devices, and you have to integrate those devices together so they work as a system. And so this can take a lot of time or a lot of cost. This is the whole subject of system integration. And we here at CCAT are taking on that work and coming up with integrated systems so different hardware devices work together so you can produce that part successfully. And then we have training from the Digital Thread Lab that we have here at CCAT, so companies can get their workforce upskilled and being able to use the technology to the best advantage. You can have a piece of software, but if you're not using every capability in that software that benefits your company, then the software is not being used optimally, and you're actually losing out on some of the cost savings that you could get if you were to use that software efficiently and to its maximum capabilities. And so then we work with the state of Connecticut, and Connecticut is really good about giving money back to manufacturing companies because Connecticut specifically knows how important it is to our economy, and they make money available. So the taxes that manufacturing companies pay to the state actually comes back to them, and the state hands out these grants so that companies can actually use the money to purchase the technologies that we're showing here. I'll hand it over to Shriniket. I gave you kind of an overview, and this is a high-level architecture of the autonomous cell that we're setting up here at CCAT. But I'll hand it over to Shriniket to describe what you're seeing here on the screen.
Thank you, Nasir. So basically, it's like Nasir said, it's a pretty high level overview of how this system is set up. So basically, I'm just gonna get the acronyms out of the way first. PLM system stands for Product Lifecycle Management System, and MES system stands for Manufacturing Execution System, just to clarify that. So basically, the MES system is, as the name suggests, controls the execution of the manufacturing. So in the yellow box, you can see edge device data, so that's machine signal data. You can see inspection data, system data, and like machine vision if that's a part of the data that you're describing, and also that. So basically, anything that's measured or calculated is part of this manufacturing execution system. So we take in all of that data, and then it's fed into the AI/ML system. So that's one half. That's the input, one of the inputs. The other input is from the PLM system. So this includes the source of truth, basically, as I call it, the model-based definition file. So we're going to have that, and then we're going to also have the machine G code. We're going to have the robot programs, all of that stuff that comes from the MBD is going to be put into their respective cells. So, and basically, let's take the CNC, for example. It has a G code for its cut paths, and then it also has all of the data coming off of it from the edge device. So both of those go in as input. The CNC machine does its thing, it cuts apart. And the AI/ML system is using that MES data coming off of it, and it's using that to make inferences on the product, the part quality, the cut quality. So basically, it's going to be able to, eventually, the whole point is it's going to be able to make corrective actions based off of the data it's receiving, so that any part that it's cutting, even if a tool is worn, for example, from overuse, we can extend tool use this way because we can adjust tool radius offset. So basically, we're just pushing the part further into, or pushing the tool further into the part so that it's still cutting exactly the dimensions that we need it with the tolerance we need, but it's doing it with a worn tool. So we're able to extend the tool life while also keeping part quality consistent. Yeah, that's all from me though.
Great, thank you, Shriniket. At this point, I'd like to hand it back over to Eileen. We're at the question and answer session point, and Eileen.
All right, great. So thank you all so very much. That was amazing, and especially exciting to see and have heard from both Shriniket and Maliha being newer on our team and newer in their careers. So I don't see any questions yet in the chat group, nor in the Q&A. But is there anyone out there who has a question that they'd like to throw in, or something, Shriniket, Maliha, or Nasir, that would be advice you would give to some of the interns that are on the call right now? The majority of them are in engineering majors in college, but we also have a few business or marketing or finance majors on the webinar today as well.
Sure, I see one question that came in. Prior to answering that question, though, Eileen, to your point, some, recommendations or guidance. Maliha, Shriniket, I'll let you go first if you wanted to kind of broaden the subject to these, the finance, the business side. I think it's really important to understand, we're discussing the applications in manufacturing, but AI has broad-reaching applications in almost every single field. Finance is especially, can use AI machine learning when you're doing forecasting. For example, stocks. We have so much historical data on stocks, and you have very, very sophisticated forecasting algorithms, such as long short-term memory algorithm, which will see, the last few months or last few years of the stock graph, and it will be able to actually predict the next couple months or the next couple weeks. The further out you go, the less accurate it becomes. But this is a way to do forecasting. Similarly, in just the same way as you do weather forecasting, the physics models that are used and the statistical models that are used in weather forecasting can now also leverage machine learning to do forecasting with this specific algorithm and other types of algorithms that do these forecasting predictions. I'll let Maliha and Shriniket answer from their perspectives as well before we get into. I see the questions rolling in now, so we'll get to those one by one.
I can go first. Starting off with an advice for the students coming from a recent, and I'm still a student, I'm in grad school. I would say just enjoy this time, do a lot of trial and error, try new things, experiment. This is the time that you're going to learn. And learning is like a lifetime thing, but this is the time that you can learn and fail, and it's without any consequences. Try as many new subjects as you can. In terms of AI, I feel like every field can use AI in different ways. However, I know there is a fear that AI will take over. I don't think it will, and I don't think it's happening anytime soon. Like at least like next decade, it's definitely not happening. And in my personal opinion, it's never going to happen. Um, just try things and go as be go as far as you can with your experiments. That's what I would say.
I guess if I had advice, I guess it would be to if you are afraid of AI, you should try to get a deeper understanding of what it is and isn't capable of. Because I do see a lot of, especially people in like C-suite level or just marketing, they kind of misunderstand just how powerful this tool is or what it can and can't do. There are some cases where you really just don't want to use AI at all, and it would just be better to use existing solutions that have been how it's been done for many years. And sometimes it's just not worth using that much data to train a model, using that much energy, time, labor to train a model, and then get something that could just be achieved by just math, linear algebra, good old matrix calculation. So like um if you want to use AI, I think the first step and the most important step is to understand what it can't do. And before even what it can do, what it can't do, and when you shouldn't be wasting your time trying to use it. But yeah, we can probably move into the questions now.
So the first question that I see here is, how are you implementing physics-informed AI? What I can do is I can give a response to that. There's two other questions after that. And then Shriniket, Maliha, feel free. I'll hand it off to you after that, to fill in any gaps or explain further. But physics-informed AI, so normally, as Shriniket mentioned before, we have manufacturing systems. I'm going to apply it to manufacturing, where we have machines that are producing parts, and attached to those machines, we have edge devices. And an edge device is basically an industrial PC, right? It's a fanless PC. And it has some certain kinds of software on it, and it allows you to collect data off the controller for the processes that the controller is controlling. So for example, on our CNC machine, we have 5 motors. It's a 4-axis machine, so we have X, Y, Z, and then the 4th axis motor, and then we have the spindle, so it gives us 5 motors. And we have up to 7 or 8, I think it is, different signals that we can get off of each one of those motors. And some of these signals are like the power consumed by the motor, the torque consumed, the actual position from the encoder, and we have 2 encoders for each axis. So we have encoder 1, encoder 2 position, and then there's some other kinds of signals that we get. And if we wanted to add extra sensors like vibration sensors, temperature sensors, we can feed that in to the controller and make those accessible through the edge device. All this means is that as we're producing the part, we're gathering data in real time. And when I say real time, it's like, and Shriniket mentioned, getting 92 parameters, so 92 signals once every 2 milliseconds. So every 2 milliseconds, we're getting 92 values. And if you think about it, if our manufacturing process is an hour, that's a lot of data. But we have to produce a certain number of parts. So let's say that we do a part run of 20, right? And in the run of 20 parts, we have to change the tool out sometimes because the tool is wearing out from cutting part 1 to part 5. And let's say we have to, and there's maybe let's just say 3 different tools that are used to produce this part. Tool being a cutting tool, like an end mill or a drill or something of that nature. And let's say after 5 parts, one of the tools has to be swapped out. We swap it out and we continue running the process. And then let's say another tool wears after a certain number of parts and we swap that tool out. we have to have sufficient data to be able to capture when those tool changes are necessary and how that's affecting the signal. But what that means is that we have to have a batch of parts that we run. And not all manufacturing processes have the required number of parts that they run to train an accurate enough predictive model. So there's the problem is for companies that are producing thousands of parts, yeah, they can just employ off the shelf and train predictive models and be able to benefit from it. But companies that are only producing a handful of parts, let's say 3 or 4, right? They're mostly high mix, meaning different kinds of parts. So they have a vast number of different kinds of part numbers, but they only produce, less than 5 of them or maybe less than 10 of them. They're not going to be able to use the traditional route. So what we want to do is we use what's called physics-informed AI, and we create a digital twin, right? A virtual twin of the machine. And when I say a virtual twin, I'm talking about the kinematics are exactly the same as the physical machine. The control logic is exactly the same. So the kernel, the software that's running in the virtual environment that's guiding the machine movement is exactly the same architecture that's guiding, that's on the physical machine. So when we produce a manufacturing program and we load it onto the virtual machine and we cut that part virtually, here's our opportunity to add a virtual edge device to that machine. Okay, when we add a virtual edge device to the machine, what we can do is we can synthesize, so we can virtually cut a part and we can virtually collect data on that part the same as we would do it in the real environment. But what's important here is that we calibrate our virtual edge device data to what we get physically. That's very important. So we want to make sure that it's an accurate virtual digital twin of the physical device. Once we have that, and once we're satisfied, and we do that through testing, through a specific experimentation, once we have that virtual, edge device ready for outputting data, then what we can do is we can actually virtually cut parts, and instead of physically cutting 20 parts, we virtually cut 20 parts, and then we physically cut 1 or 2 extra parts, physical parts on the machine, and we can take those 2 data sets and actually train a predictive model off of that. So we're essentially synthesizing more data in order to use the machine learning route as we can. Now, in the physical environment, as you're cutting apart, right, the tool is not wearing in the physical environment. Everything is perfect in the physical environment. This is why we need to have that calibration to the real world so that we can incorporate some of these varying conditions in the physics model. But to do that for specific parts is not practical. It's better to do it for the machine itself and for specific materials, and then using physics simulations to understand deflection, forces on the tool, things of that nature, and translate that back to the electrical load on the motors, which ultimately are output as a virtual edge device signal that we end up using in training a model. So that's what we mean by, this is how we're implementing physics-informed machine learning. There's other ways to do it, but this is how we're doing it. Shriniket, Maliha, anything that you'd want to add, please?
Yeah, I guess the third question is basically tacked on to the first question. So for anyone unaware, VVUQ stands for verification, validation, and uncertainty quantification. So physics informed ML. So Yukon is the one that has this model. And the best way to do VVUQ modeling is to we're gonna have physical data coming in from cut parts from our site. So we're cutting these parts on our CNC. And we can do a simple statistical analysis to see if the parameters from the simulated cut and the actual physical cut are within expected what's the word? Expected ranges. So basically, if we're expecting it to be like, we could say maybe a 95% confidence interval of some sort, and we can just do a statistical analysis. should be the simplest and most intuitive way to tackle that.
So I want to be a little sensitive to time. We've already gone over by a moment or two, and I have one or two wrap-up slides, but Nasir, maybe could you or Maliha or Shriniket take the second question? When will US manufacturing see Industry 4.0 as a standard for future businesses?
I can try to answer that as quickly as I can. So currently, from what I've seen working here, there's a lot of places, especially small and medium manufacturers, which we work with the most at CCAT, that haven't even adopted Industry 3.0 yet. So the difference between Industry 3.0 and 4.0 is basically the digital automation. So and digital industrial technology, cyber physical systems, that type of thing. So it's pretty difficult to say because as for standard, if you mean for large companies, it's far easier for them to implement Industry 4.0 because there's a scaling problem. But for small companies and small businesses, small manufacturers, it can be very difficult for them to implement this because of the high upfront cost of Industry 4.0 and also the workforce training that you would need to achieve this. So for big companies, I'd say they're almost already there. Basically, I'd say 5 years is a perfectly fine assumption, but for small, medium manufacturers, it's really difficult to say.
Yeah, I'll just add to it as in my prediction is probably 5 years. The only reason I say that is because the rate at which we're technology adoption is the challenge, as rightfully as Shriniket mentioned. It's, you know, we can show the value of the technology day in and day out, but until it's adopted. But what's important is the standards are coming out, right? We have ISO 23247, we have Step 42, we have QIF, we have neutral MBD formats, and those formats actually enable digital thread workflows. And then now with the proliferation of edge devices, with cloud computing, with AI infrastructure as a service or software as a service, you know, very prevalent. It's all the more affordable. There's no CapEx anymore per se, where you'd used to have to invest in technologies and then pay a yearly maintenance fee. Now it's just a yearly subscription, so your CapEx is reduced. So all the things are coming together where affordability is becoming easier, computing power is getting stronger, AI algorithms are being, you know, models are being able to be run on lower powered devices. So the way that technology is advancing, I think in the next 5 years, it will probably be, you know, if as companies are actually buying machines, these will be standard options on machines. And likely they will be adopting without even knowing it. It would be a matter of, are they using it efficiently? So I'll leave it with that. And Eileen,
Awesome.
if you want to take the next slides.
I will. If you could just forward through the next two slides, I'll just hop on this quickly. So thank you again to my peers, my colleagues who did such an amazing job today. But for all of you who are out there still on the line, we really want to have you engage additionally into the program. We have 3 tours coming up next, but you could also sign up to participate in our digital transformation or additive workflow training courses. So take a look at those. I'll send out some of the links in a follow-up email that will trail this call, likely tomorrow or early the next day. Join us in August for a social event at Bear's Barbecue in New Haven, right off 91, free parking. And definitely, like I put in the chat, please follow and engage with us on social. The Connecticut Manufacturing Interns Group is a place where you could meet and connect with both some of the other interns that have been on this call today, that you've seen at some of our other events, or some of the speakers that we've also had. And then just a reminder, in the spring, if you're a continuing student and not a senior going into your senior year, we'll have another job fair free to you and free to employers around the state in April, likely back at Quinnipiac University, and we'll host a similar program again next summer. And quickly, the next slide, please. Thank you, Nasir. So the remaining tours, on this Friday, Reno Machine in Newington, then July 24th, Bigelow Tea down in Fairfield, and Farrell Pamini is the last of the tours on July 31st before the end of summer networking event. So follow us, engage with us, and know that definitely the amazing speakers you heard today would be open to you connecting with them on LinkedIn. And certainly I can help connect you if you have further questions, or if your dialogue with your employer leads to desire for more exploration. That's why we're here. And that's why these experts that you learned from today are here to help drive adoption, exploration, prototyping, any kind of support we can give, especially to the small and medium-sized manufacturers. So thank you all. And thank you so much, Nasir, Maliha, and Shriniket. Bye, everyone.
Bye, everyone.
Bye.